Hi, in this tutorial we are going to solve a question related to SN1 reactions. The question asks, you are given 4 pairs of molecules. In each case, state which molecule is expected to undergo faster SN1 reaction if same nucleophile and solvent are used. Give a brief reasoning. Let's start from the first pair. In the first pair, we have 2 halides, 2 alkyl chlorides. One is a tertiary alkyl chloride and the second is a primary alkyl chloride. Let's write this. So this one is a tertiary alkyl chloride and the second one is a primary alkyl chloride. When they undergo SN1 reaction, they will produce carbocations, and tertiary alkyl chloride is going to generate a tertiary carbocation, and primary alkyl chloride is going to generate a primary alkyl carbocation. So we know that in SN1 reaction, the order of reactivity is this. Tertiary is more reactive than secondary, then primary, then methyl. And let's look at here. This is going to generate a tertiary carbocation and this will generate a primary carbocation. We expect that A is going to react faster than B. Let's analyze this situation in a molecular model. Here in this model we have T-butyl chloride, and if T-butyl chloride undergoes an SN1 reaction, it is going to have 2 steps. In the first step, it will generate a carbocation plus the leaving group, and then in the second step, the nucleophile will attach itself to the carbocation. Let's see how the carbocation formation occurs. So basically the leaving group is leaving and generating, let's one more time look at. The leaving group is leaving. Okay, let's look at here. The leaving group left and we formed a planar carbocation. As you remember, the nucleophilic attack will occur to the carbocation, and it can occur from both sides of carbocation. For that reason, we always get a racemic mixture if we start with a chiral halide. Okay, so what affects the rate of SN1 reactions? Basically, the stability of carbocation and also the stability of leaving group. So both factors will affect the rate of SN1 reactions. Let's look at the second case. So we concluded in the first case that this molecule in A will generate a tertiary carbocation, and in the B it's going to generate a primary carbocation. A is going to react faster than B. Let's continue with B. In B we have an alkyl iodide here, an alkyl chloride, and both of them are primary. Let's write. So this is a primary iodide and this is a primary chloride, and the substrate effect both will be the same. When both molecules undergo SN1 reaction, both will produce primary carbocations. So in terms of stability of carbocations, they will have the same the same factor. But since they have different leaving groups, leaving group will affect rate of reaction. We know that from SN1 and SN2 reactions, better leaving groups react faster in SN or nucleophilic substitution reactions. So which groups are better leaving groups? The groups that can stabilize the developing negative charge during the transition state. So again, which groups can stabilize the negative charge better? The groups with bigger sizes. So basically iodine, let's write here, iodine is a better leaving group than chlorine. For that reason, A is going to react faster than B. Let's look at the next option. In the next option, we have two alkyl bromide, and this one is a secondary alkyl bromide. Let's write here, the structure is secondary, and this molecule in B is also a secondary bromide. But the difference between them is there is an aromatic ring next to the carbon bearing the leaving group. So let's just look at the structures of carbocations they will produce during SN1 reactions. The first molecule will have this carbocation, and the second molecule will generate this carbocation. And the question is this: which carbocation will be more stable? The carbocation produced from B will be more stable because this is a benzylic carbocation. Let's write here, it's a benzylic carbocation. Why benzylic carbocations are more stable? Because we can write 4 resonance form for this carbocation. If you imagine that this is a double bond and this is a single bond and there is a positive charge here, we can write a resonance form and move positive charge here. Then the same positive charge can move to here because it has also a next double bond, and it can move also here. So basically together with this structure we have 3 other resonance forms, and this will create, or this will contribute to stability of this cation. So since B is going to produce more stable carbocation, it's going to react faster in SN1 reactions than A. So let's write here, B will react faster than A. Let's look at the last pair. In the last pair we have 2 alkyl chloride. Let's write here, this is a secondary chloride, alkyl chloride. This is also a secondary chloride. So basically in terms of structure, substrate structure, they are similar. Let's look at what kind of carbocation they will produce during the SN1 reaction. This molecule at A is going to produce a carbocation which is here, and that will be a double bond, and the other one is going to generate a similar carbocation, but it doesn't have any alkene functionality. As you remember, when we have a double bond next to a carbocation, we can have resonance forms. As you remember from the benzylic carbocation, we have the same situation here, even though both of them are secondary and secondary carbocations. The first carbocation produced from A will be more stable because of the resonance effect. So if we move double bond here, the positive charge will move to this carbon, and basically we are delocalizing the positive charge, and it gives rise to more stability. So basically this carbocation is known as allylic carbocation. So let's write A is going to react faster than B because A is going to produce more stable carbocation. Thank you so much for watching.